Q#, now in dark mode. I just played with that. I don't know if it's better to read it this way. Anyway, Pauli measurements. That's what we're gonna do today in this video. And I'm not so sure I'm gonna learn anything out of this. I'm just doing it out of routine. Every time I read something. So one of the good things about building intuition is that, one of the good ways to build intuition is you read the same thing all over and over again, and then sometimes you just find nuances that you didn't find before, like I mentioned in the in the 2-qubit video. And here I'm hoping that maybe will happen something similar. We'll see. Pauli measurements. In the previous discussions, we have focused on computational basis measurements, and there are other common measurements that occur in quantum computing for an additional perspective. The one is Pauli measurements. I find it a bit awkward just because I have the perspective of having gone through those concepts before, but I find it a bit awkward that the guide approaches this topic from the measurements concept. And I get it, it's really important, the basis in which a qubit is measured. But I like, intuitively, for me, it's easier to understand the whole thing from a just rotations perspective or operations perspective. So you just apply operations and then you measure. There's just one measurement operation at the end of the day, right? It's just that you change it to manipulate where the certainty and the uncertainty is. But that doesn't help at all because you don't see this graphically here either. And it's just confusing. Pauli measurements, it's just confusing. But let's go ahead. So Burr suggests X, Y, Z. And so for discussing measurements in terms of Pauli operators is especially common in the subfield of quantum error correction. We don't care about this right now. In Q#, we follow a similar convention. We now explain this alternative view of measurements. Okay, so that's their alternative view of measurements. Before delving into details on how to think of Pauli measurement, it is useful to think about what measuring a single qubit inside a quantum computer does to the quantum state. Imagine that we have the n-qubit quantum state. Then measuring one qubit immediately rules out half of the 2 to the power of n possibilities that state could be in. And that's what we've seen. That was one of the things that it's sort of a fresh perspective into that. It's okay, I have to admit, that's okay. Let's keep reading. In other words, the measurement projects the quantum state into one of the 2 half spaces. We can generalize the way we think about measurement to reflect this. Yeah, okay. It's another way of seeing that. That just makes it more confusing because every single guide has its own different view on how to interpret something, and it just makes it difficult to build intuition. So you gotta find your whatever feeds your mind best, I guess. One way of doing this is through a matrix, just 2 unique eigenvalues taken by the convention B plus minus 1. So that would be the Z. The Z matrix has 2 eigenvectors, blah, blah, blah. We measure the qubit in. Thus, if we measure the qubit and obtain 0, we are in the plus 1 eigenstate, the set of all vectors that are formed of sums of eigenvectors with only positive or only negative eigenvalues of the operator and the eigenspace of Z. It's just, like, it really discourages people to keep learning just because because of the formalism, you make it complicated. You make it just boring for the average Joe, which it makes sense. But if you want to help people build intuition fast, people are going to trust that you're not fooling them. So you don't have to prove, or you don't have to dive into certain details. Yeah, but I guess I know. Okay, I'll just shut up and go ahead. Of course, there's informations that also has this criteria. The state could also consider matrix for any unitary matrix to give a matrix that defines the 2 outcomes of a measurement. The idea of Pauli measurements references by identifying X, Y, Z measurements, including measurements that one could do again from convenience. That is, using the language measure Y is equivalent to applying HS. Okay, HS transpose. I think that's what it means. Then measuring the computational basis, and then measuring in the computational basis, where S is the so-called phase gate given by this. Okay. It is also equivalent to apply H S transpose to the quantum state vector and then measuring Z. Oh, really? That's what I mean. The correct state would then be found by transforming back to the computational basis, which, yeah. Oh, yeah. Then you apply, yeah. That's then you just apply them in reverse. It feels not needed for intuition, so I'm gonna skip that. Measurement, I mean, we'll see, because some of those things are indeed important or relevant, and if you come with zero background, completely, you're probably gonna, because I'm skipping those things. I'm just scanning those things. I'm going through those things quickly because I have done this before, and what I'm trying to do is I'm trying to gain new perspectives into the same topics, which then help to sort of shape my intuition, and hopefully learn something useful that I can then use. Definitely similar as seen for that's a product of oh, okay. Wait a second. That looks like a sort of a cheat sheet. As before, any unitary transformation of such matrices is goes to half spaces labeled. It just feels like this is not needed. It not needed to just read all that stuff. Okay. X1, Hadamard 1, Y is HS. So those are the equivalents. Boo. Maybe I should read that. As before, any unitary transformation of such matrices also describes two half spaces labeled by plus minus 1 eigenvalues. For example, X tensor product X equals H tensor product H Z Z H H from the identity that Z equals HXH, similar to the 1 qubit case. All 2 qubit Pauli measurements can be written as this for the 4x4 unitary matrices U. We enumerate the transformations in the following table, where we introduce, for convenience, the swap gate, which swaps qubits 0 and 1. And the swap is C naught, the control knot between 0 and 1, the control knot between 1 and 0, and the control knot between 0 and 1. And that kind of swaps the qubits. Pauli measurement. So I get it. That sort of summarizes on other ways to see those measurements, right? For example, the measurement, this X tensor product Z, it's the same as a C naught. But it doesn't. I don't see the utility of that yet. Here the gate C naught P is for the following reason: each Pauli measurement that does not include the 1 matrix is equivalent to a unitary. The eigenvalues is a compromise. Once to be measured, we can recover the entity in a half space, which is equivalent to the Pauli operator. I shall note, while it may be tempting to assume that measuring ZZ is the same as measuring Z1 and 1Z, this assumption would be false. The reason is that measuring ZZ projects the quantum state into either the +1 or -1 eigenstates of these operators. Measuring Z1 and then Z projects the quantum state vector first into a half space and then to another half space. In Q-sharp, such measurements return J if the measurement yields a result in the eigenspace of sine -1 to the power of J. Having this as a built-in feature in Q-sharp is helpful because measuring... Okay, so it's the first time that we talked about Q-sharp actually already in here, but that seems... The whole thing here seems so far useless. To me, at least to my intuition, okay? it is my opinion. It's just into my intuition. I mean, I learned about the polygates X, Y, and Z as gates that operate on qubits, and then um, they are just changing manipulating the state of one or many qubits. One qubit in this case, yeah, we can just apply it to many qubits. Um, but I don't get the sense of that. I don't get the sense of seeing that as measurements. I don't know why this is useful intuitively. I understand what they're trying to say. They're trying to say you can take a look at those things from. So let's think about measurements this way. So maybe a measurement is when you project a qubit into a particular space or into a particular whatever dimension from those three. But and then there's here a bunch of equivalences, and it says that in Q-sharp, such measurements return J if the measurement yields a result in the eigenspace assigned -1 to the power J. Having this as a built-in feature in Q-sharp is helpful because measuring such operators requires long chains of controlled NOT gates and Bayes transformation to describe the diagonalizing U gate needed to express the operation as a tensor product Z and 1. By simply being able to specify that you wish to do one of these predefined measurements. Oh, I think I know what they. You don't need to worry about how to transform your basis such that computational basis measurement provides the necessary information. Okay, so this seems to be. Okay, then you should just put this them paragraph in the very top, or have it explained in a way that it's easy to understand, and just drop the math before and all this other stuff, and half the people won't even scroll down that far. Okay, but that's helpful. So okay, let me explain. Sorry. So what I'm just to myself see if I understand this well. So basically, what they're doing here is Q sharp is saying. So that's how like you've got a state that encodes a bunch of like different information. So and if you wanna measure certain information within that state, then mathematically speaking, you are projecting that information into one of the measurement bases. Um, and usually that requires a lot of. It's complex to do in a quantum circuit because you have to. You see, it's just funny because this is just before the circuits chapter anyway. But you have to do a bunch of operations that might not be so obvious to remember. So what they are saying is with Q sharp, you can just tell us where do you want to project, and we're going to do it for you. So it's just a way of making that easier. I think that's what this means, which is helpful. It's helpful from a Q sharp. Yeah, that's helpful definitely. So esophagus measuring such operators. I'm just thinking again, see if what I said is just nonsense or it is really this way. Well, you can just, leave comments below. If I got it wrong, I can try to read it again, but I think that's what it's saying. I can try to go through that again, but basically, a long chain of control NOT gates and Bayes transformations to describe the diagnosing U gate says the operation as a tensor product of Z1. By simply being able to specify that you wish to do one of these predefined measurements, you don't need to worry about how to transform your basis such that a computational measurement provides the necessary information. That's exactly poly measurement. Okay, so basically what this is telling you, I don't quite get yet what the one means though. I understand x, z, that would be a measurement. So that would be a projection to the plane that's defined by the x by the z and the x axis in the Bloch sphere. Kind of. But the one, let's see if I can find this somewhere here. maybe just means not the plane but the actual axis. Okay, yeah, because that makes sense, because measuring the z, I know that this is just a standard measurement. The standard measurement is measuring along the z-axis. That's what everyone does. So, and this is telling that basically, and one is identity, or I'm assuming. Uh, so basically, what this means is if it's just the z-axis, then this equals to no transformation. So that's what. Okay, so that's what they're doing. That's what Q sharp is doing. Is basically um, you don't have to remember that stuff. So if you want to measure, and what they're saying is, if you want to measure, it's not the same to say measure z times one times z, because why you're talking about half planes. Well, it may be tempting to assume that measuring ZZ is the same as measuring Z1 and 1Z. This assumption would be false. The reason is that measuring ZZ, yeah, what does it mean ZZ? Projects the quantum state into either the +1 or the -1 eigenstate of these operators. Measuring Z1 and then 1Z projects the quantum state vector first into a half space of Z1 and then to a half space of 1Z. I don't quite understand that. Measuring Z1 projects the quantum state into either +1 or -1 eigenstate of these operators. Z1 half space into half space. I get it. What it means intuitively is that this basically, I think I get it, that this basically takes into consideration sort of the full plane, so to say, and that's just an axis. So you're kind of reducing the space in which you're projecting. Half space and then half space condition. I'd be curious because that's a measurement against Z. And 1Z is a swap. Oh, no, sorry. I got that wrong. Okay, now I get it. Now I get it. Okay. This is not defining whatever plane or shit. That's just, it's the first qubit and the second qubit, right? Because we're talking about 2-qubit systems here. So it's saying I want to measure the first qubit in the Z. I wanna project the first qubit to the Z axis and the second qubit and nothing in the second qubit. So I'm measuring just the first qubit. I get it. And ZZ is saying I'm measuring both qubits. Okay. Maybe.